Hello and welcome to another demonstration of our free response question. Let's jump right into it. Today we are looking at the free response question from the year 2017. Question number one. We are given a table, as you can see here. Lovely. We're given a table of values, and this is in regards to a tank that has a height of 10 feet. The area of the horizontal cross section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for a of h are given in the table above. So a lot was said there. I retained some of that, not all of that. All right. But let's get down to the problem. Use a left Riemann sum with three subintervals indicated by the data in the table to approximate the volume of the tank. So as we know, the integral of area equals volume. So these table of values represent area. So if we find the area under this area curve, that results in volume because you're integrating area. So we need a left Riemann sum. So that means the height of the rectangle is the left hand part of the rectangle, right? Because when you have a curve, you can make a rectangle essentially one of three ways. If this is the beginning of your interval at A, and then the next step is B, you could have a rectangle that looks like that. You could have a rectangle that looks like this, where the height is the midpoint, or you could have a rectangle that looks like this, where the height is at B, right? Those are your three options, okay? So if you want a left hand Riemann sum, then you want the first one, okay? So the area of a rectangle is length times width. So the width is the distance between the 2 points. So 2 minus 0 times the height, and the height is the first value, not the second one, because you're using the left hand. 0 is left of 2. So 2 minus 0 times 50.3 plus, then do it again. 5 minus 2 times 14.4. I'm going to use parentheses instead of a times. That is more presentation friendly. Plus, then 10 minus 5 times 6.5. This is not an updated year. I think did I say 2019? I meant to say 2017. Anyway, um, I don't because this is a calculator question. I can't say with 100% certainty if we're obligated to punch this in round to the 10th place or not. Um, but that's not particularly that hard to punch in, so I'm not going to bother showing you how to punch that in. But the answer is that. Okay. I don't think you're obligated to punch that in since it's just numbers, but maybe because it's just numbers, it's wise to do so. I can double check on that later. Okay, so there's that. I hope that makes a lot of sense there. Imagining those rectangles, width, height, width, height. All right. Part B. Does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. So, as you can see here, based on my initial curve, a left Riemann sum would underestimate whatever this random curve is. This is not accurate to this drawing. I just want to stress that. It was just something I did to demonstrate. So what makes a left Riemann sum underestimate, right? What makes it underestimate? And what makes it underestimate um, is the fact that it's increasing. So if I pull up my lovely common justifications and whatnot, Let me jump to that real quick for you. Um, there is a part here where left Riemann sum underestimate. F prime of x is greater than 0 or f of x is increasing. So you are underestimating if your function is increasing and you are overestimating if your function is decreasing. Now, you could memorize that, I suppose, or again, look at what's happening here. This function is increasing, so therefore, when you choose the left, all the other points are going to be above because it's increasing. So this left-hand sum is going to underestimate. But if everything was coming down, then the left-hand sum, you'd be making all of these rectangles above the graph, okay? So we're trying to figure out, is our function increasing or decreasing? Well, each of the a values are decreasing. So because a of x is decreasing, the sum overestimates the volume. Okay? So because these values are decreasing, our rectangles are overestimating. They are above the graph. And as far as getting into the nitty-gritty of how to earn the points on that, you, if I recall correctly, let me get there. All you have to say is the fact that it's decreasing, that a of x is decreasing. Lovely. All right. Part C. Part C says the area in square feet of the horizontal cross sections at height h is modeled by the function f given by blah. Based on this model, find the volume of the tank. So we need to integrate this area. Okay, we need to integrate this area with the correct bounds. All right, that's really all it comes down to, is integrating area to find volume. So what are the appropriate bounds? Well, you know you're going from 0 to 10, all right? So you just need to say, all right, my integral from 0 to 10, and you could bother with writing out this expression, but you really don't even need to do that. You just say from 0 to 10 of f of h dh. That's all you got to say. Okay? And plug that into a calculator. So I'll go ahead and demonstrate that in the calculator. Pull that up. Sorry. Okay. So I don't know if part C needs it, but it only takes me but a second to save the function. So does it use it? Yeah, it's I'm just quickly use the model from part C. I'm just reading part D. So yeah, this is worth saving. So let's go ahead and pull up a fraction, and we're doing 50.3 over e raised to the 0.2 h plus h. Okay. And then we're going to save that, store that, I rather should say, as f of h. Okay. So then we are integrating from 0 to 10 f of h. 0 to 10 because that's just the bounds of the function that they gave us with respect to h, and we get 101.325. And this represents volume. So if the area is square feet, this is going to be feet cubed. So if I go back to my screen here, it's going to be feet cubed. Okay? Or cubic feet, if you would like. Yeah, not much else to say there. All right. It's, don't overthink what they're saying here, right? Like, we know that if you integrate the area of cross sections, the result is volume. So if they're just handing you the area of the cross section on a silver platter, don't overthink it. Okay? Water is pumped into the tank, part D. When the height of water, I'm just going to do the problem right here because there's a lot of words. Water is pumped into the tank when the height of the water is 5 feet. So H equals 5. The height is increasing at the rate of 0.26 foot per minute. So, um, I would say, how could we say that? DHDT. So I would say like at at h equals 5, dHdt equals 0.26, right? The rate, this is the rate of the height with respect to time. In other words, dHdt. That's what they just said. All right. So just kind of like writing that down and going, okay, what am I going to do with this, right? Using the model from part C, find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. Indicate units of measure. So, using the model from part C, find the rate at which the volume, so dV dt. So, volume equals the integral from 0 to h of f of t dt, right? This is the function of area, and we are integrating that from 0 to h. In the previous problem, we did 0 to 10. But generically speaking, 10 was that specific moment in time. But it could be when the height is at 1, 2, 3, 4, so 0 to h. All right? That takes a little bit of effort to write, to think like, okay, what, like, how do I represent the volume, right? The volume of the figure is from 0 to blank. So that means dV dt is equal to f of h dV, or sorry, dH dt. Now, where did that just come from? I just derived this integral. I don't know if I end up saying it in period 6, but in period 1, I took a moment on the board and I was saying like, okay, when you integrate something from, a to g of x of f of x, the derivative of that is f of g of x times g prime of x, right? Maybe you remember that period 1, and who knows, maybe you remember that period 6, or maybe you just remember it in general. Well, we're deriving this with respect to time. So the h goes into the f times the derivative of h is dH dt. So dV dt equals f of h times dH dt. And it says, find the rate at which the volume of water is changing with respect to time when the height of the water is 5. So we want to evaluate this. We want to evaluate this at h equals 5. So dV dt at h equals 5 is equal to f of 5 times, and what is dH dt? 0.26. And what is f of 5? Well, f of 5 is simply plugging 5 into the function. And as you hopefully remember, we saved f, right? We saved f. So if we go to the calculator, we're simply going to plug in f of 5 times 0.26. And the answer, 1.694. And what are the units of measure for this? This is a rate, after all, right? dV dt. It's the change in volume. So volume is cubic feet, but it's the change in volume over time. So cubic feet per, and this is in terms of hours or minutes? Minutes. So cubic feet per minute is what we just arrived at. Only at the 16-minute mark there. Pretty quick video. Feel free to go back and rewind if you missed something. Um, yeah, I feel like this is an easier pre-response question, and I'm sorry if that rubs you the wrong way, but I do think this one is a bit on the more straightforward side. I would say D is certainly the toughest because, especially for us, it's been a minute since we've talked related rates, the whole DT thing. If you recall, if you're still watching this, I do have a full length video where I did every single problem from our related rates assignment back in the day. So that's like an hour long video, and you can peruse that at your leisure and find some highlights there. Um, but yeah. All right. Thanks for watching. Appreciate your time, and I'll catch you in the next one.